Welcome back everyone. Welcome back to this particular lecture of Unit 3 called DC motor. So DC motor is an electric motor that converts the electrical energy to the mechanical energy, just opposite to the DC generator. In DC generator we have seen it converts the mechanical energy to the electrical energy, but DC motor it has the electrical input and it converts the electric DC current to the rotating mechanical energy. So if you look at the construction of the DC motor, it is almost similar to the DC generator. The outer part of the DC motor is called the yoke or frame, and the main function of the yoke or frame is to protect the inner components of the DC motor. So it mainly acts as the protecting shield. Then as we move inside, we have the stator part. DC motor, it consists also two parts. One is the stator, which is the stationary part or the fixed part of the DC motor, and another part is the rotor, which is the rotating or the moving part of the DC motor. Now the stator part of the DC motor, it mainly provides the magnetic field. Okay. Now if you observe this red color here, these red colored portions, they are the field poles. Now these field poles are made up of the special magnetic materials, which is the silicon steel. Okay. Now these silicon steel, they provide very high permeability and low hysteresis loss. High permeability means if a magnetic material, if it is having high permeability, means they allow the magnetic field to pass through it very easily. And if a magnetic material is having very low hysteresis loss, means when a magnetic material it is getting magnetized or demagnetized, the energy loss as heat will be very less if the hysteresis loss is low. So that's why we have to carefully select these field materials. Okay. Now on these field poles we have the field windings. Now if we energize these field windings, suppose if you are giving some DC current to the field windings, well, what will happen? These field poles, they will get magnetized. Okay. Now if you notice, there is a gap between these field poles and the rotating part at each side. Okay. So in this gap is called the air gap, and if you notice specifically, the edge of these field poles, they are in the form of horseshoe shaped. So why this specific shape? So that uniform flux distribution, magnetic flux distribution is maintained in these air gaps. Okay. Now if we move inside, then we have the rotor or the rotating or the moving part of my DC motor. Now this rotor is called the armature. If you notice, the outer edges of the armature, we have some slots. Okay. Now in these slots we have the armature winding. We have the armature winding. Now this armature is nothing but a cylinder of the magnetic lamination that are insulated from each other. Okay. And inside the armature we have this commutator. This is called the commutator. Okay. Now this commutator, this is also a cylindrical structure, and it is formed by stacking the copper segments together, and they are insulated from each other using mica. Okay. Now in this commutator, what it does, this commutator is basically, the primary function of the commutator is to provide or supply the electric current to the armature winding. Okay. Now there is a brush, it is not shown here. There is a brush which is connected to the commutator, not connected, rather the brush is touched to the commutator. Okay, this brush is usually made up of graphite or carbon brush. So this brush, what it does, this brush, they basically make sure the electric current, or they supply the electric current from the external circuit to the armature winding. So both of these commutator and the brush, they they transmit the electric power from the external circuit to the armature winding. Okay, so this is all about the construction of the DC motor. Now, if we look at the working principle of the DC motor, now we have seen these field poles here, right? Red color field poles. When we energize these field poles, they will act as a magnet. So let's say this is the north pole of the magnet, this is the south pole of the magnet. Now, if we keep a rectangular loop of a current carrying conductor instead of a single current carrying conductor, then what will happen? Suppose this is my rectangular loop of the current carrying conductor. We are placing it in a magnetic field. So what will happen? As per Faraday's law of electromagnetic induction, what will happen? Some EMF, as per the Faraday's law of electromagnetic induction, when we place this rectangular loop within the magnetic field, what will happen? Some EMF will get induced, right, in each arm of this rectangular loop, and the current starts flowing, right, through this loop. Now, but each arm, the current that is flowing through this each arm, what will happen? The direction of these currents are not same. Okay, now when we place these rectangular current carrying loop within these magnet, within these field poles of the magnet, it experiences a force. Okay, and the direction of the force at each arm of this rectangular loop, it is not same. The magnitude of the force is same, but the direction is not same. Now, if we want to find out the direction of the force at each arm of this rectangular loop, what is the way out? We have to use the Fleming's left hand rule. What does it say? If we place, this is our index finger, this is our middle finger, and this is the thumb. So what does the Fleming's left hand rule says? If the index finger, if it points out towards a magnetic field direction, if the middle finger, it points out to the direction of the current, then this thumb, it will give the direction of the force, provided all these three, they are perpendicular to each other. Now see, suppose this pink color conductor, the current, this arrow, they signify the direction of the current. So for this pink color wire, the current is going inside. The current is going inside, and the direction of the magnetic field is from right to left, from north to south. Okay, direction of the magnetic field is from north to south. In this condition, what will be my direction of the force? As per Fleming's left hand rule, it will be upward direction. Okay, now come to this blue color arm. In this arm, the current is outward direction, and same, the magnetic field is from left to right. In this condition, my magnetic force on this specific arm will be downward direction. Now what about this arm? What about this arm and this arm? Okay, in this arm, we can see the current is flowing from left to right, and the magnetic field is from right to left. That means the direction of current and magnetic field, they are opposite but parallel to each other, and we know the cross product of two parallel or anti-parallel vector is 0. Okay, so in this case, here also it will be the same. Both the direction of the current and the magnetic field, they are parallel to each other. That is why the force acting on this arm will be 0. That means in this case, suppose I have a rectangular box. So at the left side of the rectangular box, the force is acting upwards, and at the right side of the rectangular box the force is acting downwards. So in this case my rectangular box will start rotating in the clockwise direction. Okay, so this loop will start rotating in the clockwise direction. Okay, it will start rotating. Now if we supply this, you can consider this is my armature. Okay, now with this armature we have this commutator connected. This commutator is nothing but a split ring. We can see this is a pink color metallic ring, this is a blue color metallic ring, and there is some gap between them. And with this commutator we have the brushes, graphite or carbon brushes. These brushes, they are not connecting to the connected to the commutator, rather they are touching to the commutator. Okay, suppose you have a toothbrush and you are touching the toothbrush to some metallic ring. So if you rotate the metallic ring, what will happen? Will the brush rotate? No, rather the brush will slip on the ring. Okay, same thing will happen here. Now if you connect this through a battery, the current will start flowing like this way. They will come to the brush through the commutator, they will enter to the armature, and it will flow through the armature, and then it will again come out like this way. Okay, so it will form a closed circuit. Okay, now what's happening here, when you are placing this rectangular loop, current carrying loop inside this magnetic field, so it will experience a force, and the direction of the force we are calculating from the Fleming's left hand rule. And in this condition, in this position, this rectangular loop is continuously rotating in the magnetic field. So once this armature, it starts rotating in the magnetic field, what will happen? It will, as per Faraday's law of electromagnetic induction, some EMF will get induced in it. And once this armature, it starts rotating in the magnetic field, it will start cutting the magnetic field. And as per Faraday's law of electromagnetic induction, some EMF will get induced in the armature conductor, and this EMF is called the back EMF. Okay, and the direction of the back EMF, it is such that it opposes the armature current. Okay, now so what is the force experienced by this rectangular loop when it is placed inside this magnetic field? It is F equals to BIL Newton. Okay, where B is the magnetic field, I is the current flowing through the armature conductor, L is the length of the conductor. Okay, now what happens? Suppose this is my armature. This is my armature. What I told, when this armature starts rotating, it will start cutting the magnetic field of these field poles. Okay, now as a result, some EMF will get induced in this armature, which is called the back EMF, in short EB, and the direction of this EB will be opposite to the armature current. Okay, now what is happening? You have a supply here. This supply you are giving, from this supply the electric current, it is flowing through, coming to this brush, and then it is coming to the armature. Okay, this brush and the commutator, they are basically supplying the electric current to the armature conductor. Okay, now in parallel to this armature conductor we have the field winding. Okay, now the current, when it is coming from the supply, it is getting divided. Some current, some part of this total current, which is called the ISH, it is flowing through this shunt field winding, and rest of the current, it is flowing through the armature, which is called the armature current. Okay, now If we write down the expression of the back EMF EB, it is represented as EB equals to phi n ZB by 60A. What is phi? Phi is the magnetic flux produced. N is the speed of the rotor in RPM or revolutions per minute. Z is the total number of conductors. P is the total number of poles, and A is the number of parallel path. Okay. Now, this is the simplified circuit of the back EMF. So, what we can observe here in the armature, we have this armature resistance and this back EMF, and this is the brush. Okay, and this is the armature current flowing from the supply. So, this total supply, it should be very much larger than this drop across the armature resistance, the back EMF, as well as the brush. Okay, so we can write the total voltage drop V equals to EB plus IARA plus VBR. Okay, now this brush drop is very less. We can neglect this brush drop. So from here, what we can write, IA equals to V minus EB by RA. So we can see here, if the speed of the armature is high, the back EMF EB will be high, right? Now, if the back EMF EB is high, from this equation, what happens? The armature current will be less, right? Now, again, if the speed of the armature is low, back EMF EB will be less, and if back EMF EB is less, then what will happen? The armature current will be high. As a result, torque will be high, and that armature will start rotating within the magnetic field of the stator.